Yes, perfect. Now we see you. Great. So, well, I'm very happy to introduce Jiahui. Okay, Jiahui is a first-year PhD student working the artistic project, and she's doing a lot of great stuff by combining experiments and also modeling in relation to battery manufacturing, right? And well, she's going to share, I think, nice thoughts that she had actually during the first time of PhD that are very useful for the interpretation of experimental data that we are acquiring in the project. So Jiahui, so the floor is yours.
Okay, thank you. Hello everyone, my name is Jiahui. I am a first-year PhD student of the artistic project. Today, the topic I will talk about is the useful tips for electrode preparation and microstructure characterization. So first of all, I would like to introduce myself to all of you briefly. I work in the ERC-ARTISTIC. It's a laboratory located in Amiens, France. Our laboratory focuses on the energy storage and the convention. My research direction is a battery optimization through modeling of the manufacturing process and the electrode architecture characterization using XCT and FIPSEM. So I would like to begin with our artistic project. The object of our project is to develop a digital twins of lithium-ion battery manufacturing process. We combined a set of physical-based models that reproduce different stages of the manufacturing process and data from the experimental representation together with the machine learning. Supported by the experimental data, the cross-grain molecular dynamic model, the discrete element model, the lattice Boltzmann model, and the continuum modeling are used to simulate the slurry preparation, coating, and the drying of the electrode, calendaring, electrolyte filling process, and the battery electrochemical performance. So at the same time, the data mining tools and the artificial intelligence machine learning models are developed to find out the interdependence between the experimental parameter and for inverse design. Today, I will focus on the experimental characterization and show you how we get an electrode in our lab and some of the microstructure characterization models method we are using. So in our laboratory, from the active material powder to the electrode applied in a lithium-ion battery, there are three main steps: slurry preparation, slurry coating, and solvent evaporation, the electrode calendaring. All of these three steps can influence on the electrode microstructure. In order to optimize the electrode, we need to adjust the formulation of the slurry. That means the ratio between the active materials, the conductive additives, and the binders. Also, we need to decide the solid content, which means the solid mass in the slurry, so as to influence the coating process. The goal of this step is to get as high as possible active material mass ratio to get a higher battery capacity, and also we need to make sure the electrode structure is stable and as homogeneous as possible. So the two commonly used method of slurry mixing is the ball milling mixer and the hydrodynamic shear-based mixer. Here in our lab, we use the hydrodynamic shear-based mixing. The coating process consists of casting the slurry to a current collector and the evaporation of the solvent in the slurry. For cathode, the aluminum foil is used as the current collector, and for the anode, we use the copper foil. The commonly used coating method include the Dr. Blood, slot die, and the coma coater. in our lab, in our project, we use the coma coater to do the coating. Then the electrode will be calendared. The shape and the position of the particle will be changed and reorganized under a certain pressure and the temperature. Before and after the calendaring process, the mass and the thickness of the electrode should be measured for studying the geometry and the property. So for the electrode preparation process, an innovative virtual augmented reality software is developed for immersive and inter-reactor data visualization and simulation. This will be introduced in detail by Professor Alejandro Franco on Friday afternoon. As for the slurry preparation and the formulation part, at first, the powder of the active materials, carbon and the binders are weighed at a certain ratio and premixed for 2 hours. Then we replace the well-mixed dry powder in the dispermat and add the solvent based on the solid content and mix them for 2 hours at a relative high rotation rate. For the NMC slurry we prepared in the lab, we used 2000 RPM. In addition to the slurry used for coating, a small amount of the slurry will be used for rheology testing and density measurement. These two measurement results will be used to conform the CGMD model, the CGMD slurry model. At the same time, the rheology help us to have a comprehensive consideration of the production process and the battery performance, and help us to find out the most suitable formulation in the manufacturing process. Dr. Emiliano Primo gave us a detailed presentation on this topic in last year's artistic webinar. The video can be found in our website. Here's a video showing the well-mixed slurry. The small recipient is usually used for small amount slurry mixing, which has a solid mass around 40 grams. We use a coma coater to do the coating. As demonstrated in the figures, the slurry passed a coma gap and be casted on the current collector. Sorry. As the roller rotated, it is casted on the current collector. The thickness of the electrode can be adjusted by changing the coma gap here, and the gap we often used is 200 to 300 micrometer. The shear rate between the coma gap can be calculated by this formula. When the coating speed is 0.3 meter per minute, the shear rate is about 60 to 25 per second. Proper viscosity is one of the key for the electrode not to have defect. After casting on the current collector, the electrode with the current collector will pass to 2 ovens. We can change the temperature and here, and we can change the temperature of the 2 ovens here. So in the panel, we can also change another parameters like the roller gap and the rolling speed. The evaporation of the solvent in the slurry can influence the microstructure of the electrode. Here is a short video to show the slurry coating process. So the slurry was casted on the current collector and moved as the roller rotate. after passing two ovens, the electrode come out the other side of the coater. So now here is the dry electrode. The calendaring is a critical step in the lithium-ion battery production. It reduces the electrode thickness by applying a compressive irreversible deformation at the surface of the electrode. The microstructure changed because of the deformation of the polymer binder. The reduction in the electrode porosity by compacting the laminate increased the particle contact at the expense of the increase in the electrolyte resistance. The optimum calendaring condition is a trade-off between these two effects. Here we can place three different parameters on the calendaring conditions: the temperature, the calendaring speed, and the pressure. So the calendaring speed and the temperature can easily controlled on the panel. But about the pressure, we use this formula to convert the pressure to the calendar gap. So here we change the calendar gap to adjust the pressure, to control the pressure. So here we put the on-calendar electrode in the machine, and we can get the calendar electrode like this. So, and after electrode preparation, the microstructure of the electrode is going to be characterized for having an idea about the energy density and power density. When we talk about the electrode microstructure, what do we talk about? Usually we focus on the pore structure. In the pore, a solid electrode, there are several kinds of pore, like the closed pore, the open pore, and the dead end pore. The open pore are the main channels through which lithium ion can through which the lithium can pass, and the electrochemical performance take place. The dead end pore acts as the electrochemical reaction place if the lithium ion can enter this pore, but they are not suitable for the transmission. Lithium ion transmission and the reaction cannot be carried out in the dead pore, in the closed pore, because lithium ion cannot get in and out. For the pore structure of the lithium ion battery electrode, the number of the pore and the morphology of pore structure are mainly described by the parameters such as the porosity, the pore size distribution, and the tortuosity factor. The porosity and the tortuosity factor are commonly used for the simulation. During our simulation workflow, porosity plays an important role. The value is used to confirm the electrode CGMD and DEM model, and also it is an input for the electrochemical models. So how do we get a reliable experimental value that can represent the entire electrode is what we need to consider. In the literature, there are several methods. The basic method based on the geometry, mass value of the electrode, the mercury porosimetries, the SEM, the 3D FIBSEM, and the 3D computed tomography. Let's begin with the director method based on the geometry and the mass value. Here we determined the bulk values of the pore solid electrode and the volume of the solid materials without the pore. With this method, total porosity can be measured, which means the average porosity come from the open pores, closed pores, and dead-end pores. And this method is really easy to get because we just need to calculate the result by the density, by using the density of the different materials, the mass ratio, and the geometry get from the experiment. But with this method, we cannot get any information about the pore size distribution. The porosimetry is an analytical technique used to determine materials' pore structure, in particular pore size and pore size distribution by intrusion of a liquid. So the mercury as a non-weighting liquid is introduced into the pore structure with increasing pressure. The pressure applied can be conveyed to the pore diameter by this Washburn equation. Then we can get a curve of the relationship between the intrusion mercury and the pore size. We can deal with the data to, for example, differentiate the curve, and then we can get the pore size distribution. With this method, we can we can measure the open pores, the dead-end pores, and get the porosity distribution, and the pore size above 1.5 nanometer can be identified. The SEM, the percentage of the error of the pore in the SEM image and the volumetric porosity in the real electrode are considered to be equal. So we took a SEM image like this, and then we use the Fiji plugin, the trainable Weka segmentation to segment the image into two different phases, the pore phase and the active material and CBD phase. So with this method, we can get the open pore, closed pores. Sorry, here is the dead end pores and the porosity distribution. Now, under a high magnification, a pore with the minimized size of 5 nanometer can be identified. In our group, we already use these methods to study the pore size distribution under different calendaring conditions. As the accuracy of the SEM is limited, and it is a local but not global measurement, we come to the 3D X-ray computed tomography. We used a laser to cut the sample with a size of 50 micrometer. In our group, we use a convolutional neural network as a tool for segmenting the 3D great scale tomography data. So we have recently demonstrated that we can train a CNN model by giving only one labeled image and make a faster prediction of a gigabit volume. Here is the 3D volume to show the treatment. With this, this experiment was done with the Dr. Acknowledgements. With this method, the oxide percentage of the pore phase is equal to the porosity. And at present, the highest XCT resolution in the world is 20 nanometer per voxel. So ideally, pore size and shape above 20 nanometer can be identified. Also, because of the resolution, we come to, in order to study the nanopores, we introduced the FIBSEM. The nanopores is referred to a pore with nanometer size 1 to 100 nanometer. The treatment of the FIBSEM data is similar to the 3D XCT, with a resolution of 2.5 nanometer per pixel. Pore size and shape above 2.5 nanometer can be identified. In our model, due to the resolution and the calculation cost, the nanopores cannot be obtained. We need to use the nanoporosity value to confirm our model. So here I used the director model and the 3D X-ray CT to measure the porosity from the same sample. And here is the result, which are quite different. So as a conclusion, in the research, we need to choose the appropriate approach to according to our need and the advantage and the disadvantage of each methods. And what's more, it's important to use the consistent method of the simulation input and specify while presenting the result. Thank you very much for your attention.
Thank you very much, Jiahui, for the very nice presentation. So as I mentioned at the beginning, so Jiahui's work is very important to standardize the way that we characterize electrodes, because we need let's say clean parameters as an input for the model development and also for the model validation. And well, her work clearly illustrates that the characterization of porosity, for example, is something that is not trivial. So it's very technique dependent. Of course, tomography has limitations. I mean, on the characterization of the porosity, in particular, we are intending to resolve the porosity inside the carbon binder phase. But it's still a useful technique in order to validate these three-dimensional models that we are developing as the one Alan showed today.
Yes.
So Jiahui, so I think you have some questions in the. I will put one question here, so in the screen. So on slide 5, this is a question from Mikołaj Nowak. So on slide 5, you mentioned that in the second step, you mix the slurry for 2 hours at 2000 RPM. Can you increase the speed 8 times to 16 RPM and shorten the mixing time 8 times to 15 minutes? What will be the consequences? So I think it's a question from experimentalist to experimentalist.
Yes, yes.
A tough one.
Yes, it's a good question. I never tried the parameter like this. The parameter I used is from 1,500 RPM to 2,000 RPM. And it's more what to say that oftenly used in the industrial, I think, and it's optimized the parameter by the others in our project.
Great. Okay, so we have a question from Serian Su. So thank you for the talk. Can other parameters such as temperature, solution quantity play a role in the equation in slide 7, or is it an empirical one? Can you give more insight of it? Yes, I think he's referring to the equation relating the calendaring gap and the pressure. Can you hear us, Jiahui?
Yes, yes.
Yes. Okay. So I think you have a project mate helping you.
Yes.
Understanding the question. So basically, the question is:
Yes.
do you think that, for example, the roll temperature and the roll speed so will influence also the properties of the electrode upon calendaring?
I think the rolling speed will impact the calendaring process.
Yes, and I think the point of Seriang is that this equation doesn't capture that, right? I mean, you don't have the.
Sorry, I'm not very sure about what's the question. What he asked is about the equation and the other parameters. Yes.
Yes, I mean maybe Serian Su can write an extra question to clarify his question. Maybe is what I understood, but okay, because we have Margaret back.